Hey folks, let's take a look at today's lesson, which is going to be on what is called the accumulator function. Now, what that is kind of an extension of our position, velocity, acceleration problems from first semester, except we're going to be kind of doing some of the things backwards. I want to just remind you guys of a couple things. Number one, that the velocity is the derivative of the position, and that the acceleration is the derivative of the velocity. And also, if I integrate acceleration, that's going to get me velocity. And if I integrate velocity, that's going to get me position. With the accumulator function, our position is going to be defined as the integral of the given graph. So what we've got in here is a graph, and I'm telling you that this is the graph of f. Now, what we're going to talk about is, as is usual, when we talk about position, we often use the letter S. And we're going to say that our velocity is going to be represented by f of x, otherwise known as the graph in this situation. So if I am asking you what the velocity is, that's just going to be the points that are on the graph. On the other hand, if I'm asking you to find the position, we're going to need to integrate this, which means we're going to be talking about the area between the graph and the x-axis. On the other hand, if I ask you to talk about the acceleration, that's going to be the derivative of the graph, or the slope of the graph. So what we've got here is we've got our differentiable function, and the position at time t of the particle that's moving along some sort of coordinate axis is given by this function in here. But of course, we can say that we've got the information up here also. So let's try and run through a few questions. What is the particle's velocity at t equals 2? Well, since we're talking about velocity, that just is going to be information I can get from my graph, and I can say that at 2, I am looking at a velocity of -4. So far, so good. Next, I'm going to say, is the acceleration of the particle at time 2 positive or negative? And I would say that, well, what is my slope at 2? Well, my slope is going to be negative there. Okay, so got it. My slope is negative. Okay, next up, let's take a look here at what is the particle's position at time 3. Now remember, the position is going to be the integral of the velocity. So what I'm going to be doing is I'm going to say, well, I've got a nice straight line here running between 0 and 3. And I can say that if we're talking about the integral, I'm going to find the area between this line and the x-axis. So that would be in the shape of a triangle here. So I'm going to say 1/2 base times height. And we just integrate that, and we end up with an answer of -9, whatever that is. Okay, where does S have its largest value? Again, S being the position. So when do I have the largest value here? Now notice, as I take off from here, I end up going into negative values and continue to get negative values. Again, negative accumulated area, and I'm adding in a huge amount of negative area. And then I add back in some positive area there. So as it turns out, the actual largest value that S has during this time is going to come when t equals 0, because my maximum S value is going to be at 0. And so it is 0. Okay, next up, when is my acceleration 0? And I'm going to ask you to humor me and assume that my dot is just a little bit over here. And I would say, well, let's assume that I've got a slope of my graph here at 4, and I have a slope of my graph here at 8, and I'm going to assume both of those things have slopes of 0. So my acceleration would be 0 at both t equals 4 and t equals 8. Okay, next up, where is the particle moving toward and away from the origin? Again, assuming that we're starting at the origin. We're not going to do anything else today. We'll run into those a little bit later on. So I'm going to say, well, I start right away and I'm moving away from the origin because I'm moving into the negative area. My position is negative, and it keeps staying negative. So I keep moving away from the origin until I get to 7. Now at 7, I change my direction because now I'm adding an area, so I'm going to be moving towards the origin at that point. So I'm going to say I'm moving away from the origin from 0 to 7, and then I'm moving toward the origin from 7 to 11. Okay? And on what side of the origin does the particle lie at time t equals 11? And what I'm going to do is I'm basically asking you to find the net area. I'm not asking what the actual value is, but I'm going to say I've got a huge amount of negative area here, and I'm adding about a little bit of positive area there, so I end up with my overall side of the origin is, since it's negative, that's going to be the left-hand side. Okay, same sort of problem, looking a little bit different. This time it's a different graph here, and we're talking about the same thing. F is the differentiable function whose graph is shown below. And we're going to say that, well, what we're looking at here is we're going to be saying that my velocity is going to be what is graphed. And then we're going to try and do some analysis from here. It's written a little bit differently here because, again, we remember that our position is the integral of the velocity, and that I'm kind of taking the derivative of the integral to get f of x, and I'm taking the derivative of the integral. Which is kind of using the first fundamental theorem of calculus, but just writing it out so people might be able to see it a little bit differently. So let's get started. What is the particle's velocity at time t equals 4? So I'm looking at velocity, and I'm going to say my velocity is going to be 2 because this is a velocity graph. So there we go. Next up, is the acceleration of the particle at time t equals 2 going to be positive or negative? Well, my slope here, which is going to be the acceleration, is the slope of the velocity. It's positive there, so I'm going to say it's going to be positive. And let's see what else. What is my particle's position at t equals 4? Now, my position, remember, is the integral of my velocity, or the integral of my graph. So I'm just going to be looking at 1/2 base times height, since I'm forcing a nice triangle in there. And so that's just going to be 1/2 of 4 times 2, which just gets me 4. And at what time does S have its largest value? Now, again, we started here assuming that we have our position is 0, and then what happens? I'm adding in area, which means I'm moving to the right until I get to 7. So at 7, I stop adding value and I start subtracting some area. But guess what? This area is always bigger than that area, so I'm going to say my largest value is going to be when t equals 7. Okay? And when is the particle moving toward the origin and away from the origin? Okay, so we start at the origin, and then we are moving to the right until we get to here. And that means I'm moving away from the origin. And then I turn around because my area is going to be negative, and now I'm moving toward the origin from 7 to 11. So we're going to be toward the origin, okay, from 7 to 11, and away from the origin from 0 to 7. And on what side of the origin does the particle lie at time t equals 11? So I'm looking at my net. This is positive. That's a little bit less, and it's negative. I combine those together, and I end up with the positive side to the right. And on what interval is S concave up? Okay, so that's going to be pretty easy to figure out because, again, S is my position. So I'm going to be saying that it's going to be the derivative of the graph. So I'm going to say, when do I have my acceleration, or the slope of what is graphed there, being positive? I'm going to say it sure looks like I'm running in between 0 and 5, and then from 9 to 11. And we've got that in there. Okay. Well, guess what, folks? That's it for the day. I would recommend that you guys get to work on taking a look at the exit slip. You'll find that in the calendar. Understand that my expectation is some of you might struggle with it. There are some problems that are reviewing the first fundamental theorem of calculus there. That's problems 1, 2, 3, and 4. And then 5 and 6 are going to be ones that you can look at. The answers are posted so you can check things out, and I'm assuming that I might have to answer some questions then. Thanks for listening, and hopefully this makes a little bit of sense, and I'll look forward to seeing you guys again.